In the previous video tutorial, we saw how we can determine maximum stress values acting on an I-section cantilever beam using both hand calculations and Fusion 360 Finite Element Analysis software. In this video tutorial, we're going to do the same thing, except this time we're going to carry out our calculations for an encastre or built-in beam. We're working with many of the same values here as in the previous video. So we have the same load of 24.5 kilonewtons, and once again our beam is 12 meters long and the load is applied 4 meters from the left hand support. Now the major difference this time, instead of having a cantilever beam with a support just on the left hand side and a free end at the right hand side, this time we have fixed constraints or fixed supports at both the left hand and right hand end of the beam. So for an encastre or built-in beam, we have fixed supports at either end. So in practice, the beam could be inset into the supports or it could be attached directly to the supports. Now I've already carried out some calculations for this beam, and these are calculations that you've seen in an earlier tutorial. We have calculations for our left and right supports. The calculation for the left support gives a support reaction of 18,148 newtons, and the support reaction for the right hand side comes out at 6,352 newtons. Now if you're unsure how those values were calculated, then you can either check those values using the calculation on the screen there, or you can return to the earlier tutorial where there's a full demonstration on how to calculate those support reactions. Now exactly the same is true for the bending moments. We have bending moment calculations for the left and right supports, and we also have a bending moment calculation for the point of application of the load. These formulas or these calculations were also covered in the earlier tutorial. Now working with the numbers that we have here, we have a value of P of 24,500 newtons, we have a value of A of 4 meters, and we have a value of B of 8 meters. And this gives us a bending moment at the left hand support of 43,556 newton meters. At the right hand support we have a bending moment of 21,778 newton meters, and at the point of application of the load we have a bending moment of 29,037 newton meters. And just as a reminder, the value of A is the distance between the load and the left hand support, and the value of B is the distance between the load and the right hand support, like so. The overall length L in this case is 12 meters again. Now although we've carried out those calculations for the left and right hand support and the bending moment at each of those three positions, what we're really interested in is the maximum support reaction of 18,148 newtons and the maximum bending moment of 43,556 newton meters. We're going to transfer those values in a moment, and then we're going to calculate the maximum bending stress acting on this encastre beam. Now before we do that, I just want to remind you of some of the other information that we have on the screen here. We're using the same beam designation as in the previous tutorial, 356 by 127 by 39, and we said previously that that beam has an elastic section modulus of 576 centimeters cubed, as we see in the tables there. Now we also extracted some other relevant information, and this was to aid us with producing our 3D CAD model for the beam. We used values for the depth of the beam, the width of the beam, the web thickness, and the flange thickness. And we used those values to produce the cross-sectional diagram of our beam, as shown in the top right-hand corner. And then we extruded that beam cross-section in order to produce our 3D model. Okay, let's transfer our maximum reaction force and our maximum bending moment value, along with the details relating to the beam, and then we'll determine the maximum bending stress acting on this beam. Okay, so here we have all of the key information relating to our beam. And so we're going to do a couple of things here. First of all, let's highlight our maximum reaction force. Let's also highlight our maximum bending moment. Notice that this occurs at the left-hand support. So we're going to determine the maximum bending stress acting on our built-in beam, and then we're going to use numeric simulations, as we did previously, in order to confirm or aim to validate those values. So we said previously that the Z value for an I-section beam is the bending moment divided by the stress, and rearranging that, we said that the stress was equal to the bending moment over the Z value. Well, we have the maximum bending moment acting on our beam, 43,556 Newton meters, and we need to divide by the Z value, but it's the Z value in meters cubed that we need to use. Now we have our Z value on the left hand side in centimeters cubed, but recall we need to divide by 100 cubed in order to get that value in meters cubed. Dividing by 100 cubed gives us a Z value of 0.000576. So our maximum bending stress then, acting on this beam, is 75.62 megapascals. Okay, so now let's return to our beam that's already been constructed in Fusion 360. We're going to create a new static study, but this time we're going to constrain the beam at both ends to simulate or to model our encastre built-in beam. So I'm not going to repeat the demonstration of how to construct this beam. It's exactly the same as in the previous video, so if you need to reconstruct this beam or you want a reminder of how to construct the beam, then you should review the previous video. Instead, I'm going to focus specifically on setting up the static stress simulation and reviewing the results. So the first thing that we need to do is start a new study. And if we go to the top left-hand corner here and we click on Set Up New Study, once again we'll be prompted to select the type of study that we want to carry out. We're going to do a static stress simulation and we're going to click Create Study. Now you'll notice in the left-hand menu that we have Simulation 1, and this includes all of our meshes and results for the original cantilever beam. We're going to start a new study, and this time we're going to set up a new load case. Now, as in the previous video, we would move left to right along these menus, but as we said previously, we're not going to simplify the model any further. We've already removed fillets from the cross-section of the I-section beam, and we're also not going to change the study material. By default, the study material was steel, and in actual fact, reassigning the material wouldn't change the stress values, it would only change things such as the factor of safety, which define whether the beam would fail. So the first thing that we're going to select is our constraints. Now you'll recall that previously, we only constrained the left-hand end of the beam, because we wanted to simulate a cantilever beam. But this time, we're going to constrain both of the ends of the beam with a fixed constraint to simulate a built-in beam. So let's select constraints. We're going with the fixed constraint, and we're now prompted to select the target faces. We need to select two faces this time. We need to use the pan to bring the left-hand face into view. And once again, we're going to need to repeat pan and zoom to bring that face into view. Hit Escape to come out of the zoom tool or the pan tool and select the first face. We need to select the other end of the beam. So if we return to the home view by clicking the home icon, so I need to pan the opposite end of the beam into view. This time we're going to use the orbit function on the left hand side in order to rotate the beam. All I did there was hold the left mouse button as I moved the pointer. It does take a little bit of practice. And once again, by panning and zooming, we can bring that end of the beam into view. Now we need to make sure that we can select the correct face. So I'm going to hit Escape and select the right hand end of the beam this time. And we'll notice that we have two faces selected for the two ends of the beam. Let's click OK and return to our home view. The next thing we did was apply our load. And you'll recall that the type of load we used was a remote force. and we selected the top face of our model. So what Fusion has done by default is apply our remote load to the centre of that face. So we're in the correct position in the Z direction because we're on the top face, and we're in the correct position in the X direction because we're at the centre of that face at 63mm. But we don't want the distance to that point load from the left-hand support to be 6 metres. Instead, we want it to be 4 metres or 4000mm. And you'll notice that the graphic has been updated accordingly. Now, we also need to assign the magnitude of that force, 24,500 newtons. And now we can click OK. So we've applied our constraints and we've applied our load. The next step is to generate our mesh. So make sure you're under Static Stress Study 2 and right click on Mesh and select Generate Mesh. Now once again, we're going to use the default mesh for this model. We spoke in the previous video about how the different meshes can affect the accuracy of results, but here we have a relatively simple geometry and we're trying to keep things as simple as possible. Okay, the only remaining steps then are under the Solve menu. We're going to do a pre-check to make sure our beam's all fully constrained and ready for the simulation. And then again under the Solve menu, we're going to solve. Just make sure that Static Stress Study 2 is the one that's been checked, and then Solve 1 study. Okay, once the software has finished running the simulations, we can close the job status window and we can close the results detail window. We're also going to hide the load case, which is the applied force. And we're going to do that by going to our load case on the left-hand menu and clicking the eye icon. And at present, the result that's being displayed is for safety factor. We have a minimum safety factor of 3.665 on this beam, but note that that's specifically for the type of steel that was selected as the study material. Let's change that from safety factor to stress. And we notice that the maximum stress acting on the beam once again is at the left-hand support. So really, that's the primary area that we're interested in. We also have a value for the maximum stress, 56.633 megapascals, and I'm going to make a note of that value for our evaluation in a moment. So according to our simulations, the maximum bending stress acting on this beam is at the left-hand support with a magnitude of 56.633 megapascals. Now, the other piece of information that we want to extract from this simulation is the reaction force, or the maximum reaction force acting on the beam. Now, once again, we notice that the maximum reaction force is occurring at the left-hand support, and we have a value there of 5831.711 newtons. Once again, I'm going to make a note of that value so that we can transfer it across and compare with our hand calculations. Now, we could also look at the reaction force and the bending moment at the right-hand support, and we could also look at the bending moment at the point of application of the load and compare those to our hand calculations. But what we're really interested in is looking at these maximum values because it's actually the maximum bending stress occurring on the beam that would determine whether it would fail. So let's go back and compare these values with the values previously obtained from hand calculations. Okay, so I've transferred our simulation results. We have the left-hand support, 5832 newtons, and that was the maximum of the two supports. And we have our maximum bending stress of 56.633 megapascals. You'll notice that we have one piece of information missing, and at present we don't have a value for the maximum bending moment as determined from simulations. Now the reason for that is when we did the hand calculations, we first determined the maximum bending moment acting on the beam, and then we used that information to determine the maximum bending stress. However, our simulations have yielded a maximum bending stress value Therefore, we need to determine the maximum bending moment from that value. So recall that we said that Z equals m over sigma, meaning that m, the maximum bending moment, is Z, the elastic section modulus, times sigma, the stress. We have our value of Z, 0.000576, and that's in meters cubed. And we need to multiply by our bending stress, 56.633. Recall that as that is in megapascals, we need to remember to include the times 10 to the power 6, giving us a maximum bending moment then equal to 32621 Newton meters. Now note that that's occurring at the left-hand support. So what do these results demonstrate then? Well, first of all, if we look at our stress values, we can see that the stress value obtained through simulation of 56.633 megapascals is somewhat lower than the stress value obtained through hand calculations. Subsequently, that's meant that our maximum bending moment through simulation is somewhat lower than our maximum bending moment using the hand calculations. Now, what's probably more apparent is that the maximum reaction force, again at the left-hand support, using simulations, is significantly lower than the maximum support reaction using hand calculations. And we'll talk a little bit more about that in a moment. But there are some positives to take away from this. Although our stress values do differ, we said previously that the beam would fail as a result of bending stresses. It wouldn't fail as a result of the support reactions. So the fact that these two values are of the same order of magnitude does still give us some confidence in our simulation results. So although there's a difference between those values of around 30%, they are still supportive of one another because they're of a similar order of magnitude. Therefore, the same can be said for our bending moment values. Naturally, we have less confidence in our support reaction values, but let's collate the results for both our cantilever beam and our encastre beam, and then we can have some discussion around potential sources of error and discrepancies between these results. So here we have a summary of all of the results obtained from our hand calculations and our simulations. We already spoke about the significance of mesh density when we evaluated the results for our cantilever beam, and we also discussed the simplifications that we made to the beam geometry. And we was able to account for the slight differences between the results for simulations and hand calculations for the cantilever beam. We can make similar observations for the built-in beam because our stress value and our bending moment values are still relatively close to the expected results. But we need to consider what's causing these discrepancies, particularly with the reaction force. Now, one of the things that the hand calculations assume is that the force acting at the support acts directly upwards. So the assumption is that when the beam is loaded, we have a reaction force at the left and right hand side that acts directly upwards and balances the force acting downwards on the beam. However, that isn't technically true, because as we saw from our simulation results, the beam is going to deflect. So if we modify our drawing slightly, the beam is going to deflect as a result of the loads being applied. And I've exaggerated that result on the diagram. So what we notice as a result then is that the top surface of the beam is trying to pull away from the support. So the reaction force is going to need to hold that top edge in place. And at the bottom edge of the support, we see that the beam is being compressed against the support. So the reaction force is going to aim to push away against the bottom face of the beam. If we think of the impact that has on the opposite end of the beam, these two forces working in tandem are going to cause a turning moment. Now that turning moment is also going to have an impact on the reaction forces. If we consider what's happening at the other end of the beam, then we're going to have exactly the same effect, where we have tension at the top surface of the beam and compression at the bottom surface of the beam. So we're going to see an opposing turning moment acting at our left-hand support as a result of the forces at the right-hand support. So we can see that there's lots of things at play here, and there's lots of things affecting the support reaction. From our simulations, what we determined was the total support reaction at the left-hand side, rather than the vertical support reaction, or the support reaction acting directly upwards. But we can see because there's so many factors at play there, the reaction force isn't only going to act directly upwards, and some of those forces are going to aid or help to support the beam, whereas other forces and turning moments are going to oppose or place additional stresses on the beam. So just to summarise then, we can still take confidence in our simulation results and our hand calculations for both the cantilever beam, where we saw support reaction forces and stress values relatively close to one another. And we can also take confidence from our results for the built-in beam because we have stress values in the right order of magnitude. And as we mentioned, the beam would fail as a result of bending stresses. But the reason we see these discrepancies in the support reactions is because the hand calculations assume that we only have a vertical component to the reaction force, whereas in reality, we have force components in different directions, we have turning moments caused by opposing ends of the beam, and our simulation results, although they still determine the support reaction at the left-hand support, actually determines the total force rather than just the vertical component of that force. So I hope you found this video useful, and thanks for listening.